Hey guys, welcome back to Problem Up Chem. In this video, we're going to be closing out our exploration of isomerism, looking at optical isomers, how we can determine a molecule that does have optical isomers, and what are the key features of optical isomers. Before we get started though, there's a little question here that's about the geometrical isomerism that we did in the previous lesson. So first you're going to need to draw the compound, it's a cyclic compound, and then look at both isomers. Pause the video to have a go at that. So the key things you need to look at from this question are of course, molecular formula and the fact that this is cyclic. So we've got a 3-carbon ring, we add in 4 hydrogens and 2 chlorines. Now this is where the isomerism is. You know that you can't rotate around these bonds because we've got a ring structure. So if we put the chlorines both below the plane of the ring or above and below, then we get the 2 different E and Z isomers. When we go again across the double bond, we're going to have our E isomer, and when we're on the same side of the double bond, we're going to have our Z isomer. So this is going to be E12 dichlorocyclopropane, and the other is going to be Z12 dichlorocyclopropane. So as I mentioned, geometrical isomerism was the last lesson we did, and now we're looking at the other type of stereoisomerism, optical. This type of isomerism is based around what we call chirality, which comes from the Greek word chiri, which means hand. And that's because hands also have this property of chirality, or to put it more specifically, non-superimposability. That means that these cannot overlap when they're in the same place. You take your right and left hand, no matter how much you try and rotate one around the other, you can never lie all of your fingers and thumbs over each other while your hands are facing in the same direction. So any molecule containing a carbon that is attached to 4 different groups will demonstrate this property of chirality. So if a molecule contains a chiral carbon, that's a carbon with 4 different groups, it will be a chiral molecule and it will have optical isomers. So if we take the example of amino acids and take the general formula, then we can see that the central carbon has 4 different groups, if in this case the R is not a hydrogen, and we call that the chiral carbon or the chiral center. So the way we draw the isomers of this is if we draw a plane down the middle and treat it as a mirror, and then simply draw the exact mirror image, you'll see that if we try and translate the image on the right onto the image on the left, the groups on the left and right have switched sides, and that means they're now non-superimposable, which means these are 2 optical isomers. So chiral molecules have a few distinct features, the most important of which is that they have no plane of symmetry. That's going to be important when we come to identifying chiral carbons later as well. As I've said before, they're non-superimposable mirror images of each other, and remember that just means that the objects can't ever perfectly overlap with each other when they're in the same place. We call these objects enantiomers, or isomers enantiomers, and quite simply these are the 2 different optical isomers from a chiral carbon, the pair of isomers if you like. And we can differentiate these by the way they rotate plane polarized light in opposite directions. We're going to have a little look at that in a moment in more detail. And if we have a 50-50% mixture of these enantiomers, then we call that mixture a racemic mixture or a racemate mixture. So that's 50% of each of the enantiomers. And it's that opposite directions that gives these enantiomers their names based on their right or left directional spin. So we have the right hand and the left hand isomer, or the R and S isomer, sometimes called the D and L isomer, especially when we're naming sugars. However, we're not going to be looking at the nomenclature of these, as that's not required in the core component of the IB. So let's have a look at how we can go about detecting these molecules. As we've mentioned, optical isomers rotate plane polarized light in opposite directions. But what does that mean? Well, if we think about the nature of light as a wave, then we usually draw it like this, the transverse section. But if we think about it end on, we don't just get an up and down line. All around the 360 axis, we have lines that are going at all these different angles. This is normal light. So polarized light is where we pass light through a polarizing plane, and that transverse section looked at from the end now just has one plane of light. This is plane polarized light. So that plane polarized light can help us identify optical isomers. So in an apparatus called a polarimeter, we put normal light in, that goes through the polarizer, it goes through this kind of polarizing sheet, and then that plane polarized light is passed through the sample. Now when it goes through the sample, when it comes out the other side, it is going to be rotated by some factor, and the direction of the rotation tells us which isomer we have. The way we detect this by looking down the end of what is produced, if you like, down the end of the polarizer, is we have two slits that are perpendicular to each other. Now, when they are perpendicular to each other, the plane polarized light is completely dark. There is no light that gets through without the sample present. Now, when the sample is present, all of a sudden there is some rotation, and so therefore some light gets through this gap. And so if we rotate the detector to a certain degree, we will then end up with it going black again, and that tells us the angle. So as I've mentioned before, pure solutions, or solutions of one isomer, will obviously rotate in one direction, and samples of the opposite isomer will rotate in the other direction. But this still doesn't mean we'll always detect optical isomerism, because if we have a racemate mixture, a 50-50 of each isomer, we actually will detect no rotation of plane polarized light, as half of the sample will cancel out the rotation of the other half. Time for a couple of quick questions then. First question, what makes a molecule optically active? Pause the video. Pop 'em up! So, it's chirality, or a chiral center, a carbon with 4 different groups attached to it. Next question, how do we go about detecting optical isomers? Pause the video. Pop 'em up! Of course, we rotate plane polarized light in opposite directions, and we use a polarimeter for that. So, as we've discussed, the only way, the physical property we can use to differentiate between these kind of isomers is rotating plane polarized light in opposite directions. However, biological systems are much more sensitive to this form of isomerism, because although enantiomers have basically the same physical and chemical properties in 2D systems, when we consider them in a biological context, the main mechanism by which these reactions will occur is through the action of enzymes. And the key part of an enzyme is its active site, and specifically how the active site has a 3D specificity. We can have an active site of an enzyme where the reaction occurs, the substrate is broken down, and we can put the substrate in. However, if we take the substrate with exactly the same composition and just rotate one part of the molecule around, all of a sudden this will not fit into the active site, and the reaction will not be able to be catalyzed by the enzyme. Unfortunately, this discovery is actually mired in tragedy when in the 1960s there were many babies being born with what's called truncated limbs, which is a genetic disability that causes deformation in the limbs, incredibly high rate, and the culprit was found to be a drug called thalidomide, which treats morning sickness. And in a cruel twist of fate, this was marketed as a racemic mixture because it was unknown about the different types of isomer that could be formed. And one of the isomers, the R isomer, was completely fine, treated morning sickness and had no effects on unborn children. And the S isomer, unfortunately, had the effect of causing these genetic deformations. So, how can we determine chiral centers in molecules we may have produced or may be presented with in an exam question? Well, we've got to remember carbons with 4 different groups connected are going to be chiral and produce optical isomers. So, the first step you want to take here is you want to identify all the sp3 hybridized carbons in a molecule. That's all the carbons that have 4 single bonds to another atom. So if we look at this molecule here, we'll see we have 4 sp3 hybridized carbons down the backbone. Working from the top down, we can see that the top 2 carbons both have multiple hydrogen groups, therefore cannot be chiral. However, when we get to the 3rd carbon, we can actually see that we have a CH3, an OH, a hydrogen, and this C2H5 group. That's 4 different groups attached to that carbon. Therefore, that carbon would be a chiral center. Of course, the last carbon, another CH3 group, would not be chiral. So we can draw that molecule out in a 3D projection, and then draw our mirror and complete our 3D projection, and we'll see that we have made both enantiomers in this drawing. Now, if we have a molecule that is ringed structure and doesn't have the open chain, we can still follow the idea that the molecule must have no planes of symmetry in order to be able to determine if we have a chiral center. For example, if we have a look at thalidomide, we can go through and we can identify all of the sp2 hybridized, but there's not actually that many sp3 hybridized carbons here at all, just 3 of them. And 2 of those are going to be CH2 groups, so they're not going to be of any use to us. So it's only this 1 carbon we have remaining that is a potential for a chiral carbon. So if we have a look at this carbon and we look at the 4 different groups that are attached, instead of following out a chain on one side or the other, we're going to draw a line through the molecule and have a look to see if the molecule is reflected through that carbon. And what we see is there is no plane of symmetry. Now, if there's no plane of symmetry, we must have a non-superimposable molecule. So indeed, this carbon is a chiral center because there is no plane of symmetry, making the molecule optically active. So remember, looking at another example, the first thing I want to do is to find all my sp3 hybridized carbons. So I have 4 in this molecule. I have the carbon that's attached to the CH2, attached to the NH2, the other CH2, and attached to the NH bond just below that. Our CH2 groups are out because they have 2 of the same group. And then if we have a look at these 2 in turn, we see that this one has 3 different groups, and not forgetting our hydrogen, so that would indeed be a chiral center. And our other one, we circle our 3 other larger groups, and not forgetting we would also have a hydrogen. So in this case, both this carbon and the other carbon here are chiral centers. Now, once you've determined the chiral center, which we can do here with 2-bromobutane, we want to make sure that we can definitely draw the enantiomers. So again, I find all my sp3 hybridized carbons, and then I instantly discount CH3 and CH2 groups, leaving me only 1 carbon here, which I can see definitely has 4 different groups. This group here, so we can draw that CH3, has the bromine group up top, so I'm going to draw that bromine group up here. Then it has this C2H5 group out to the right hand side, And of course, it has the hydrogen that's not shown in this formula. And if I want to draw the enantiomer, remember, just draw a mirror and then make the exact copy on the right hand side. This is always going to give you the correct 3D projection of the enantiomer. Okay, let's finish up with some questions. First one, in this molecule, identify the chiral center. Pause the video, give yourself a moment for that. Pop them up. So, of course, find all the sp3 hybridized, discount CH2 and CH3 groups. That leaves us just this carbon here. Next question. Draw both enantiomers of this molecule using 3D projections. Pause the video for that. Pop them up. So once you've identified that it's the carbon attached to the cyanide group, you're just going to follow the same principles. Draw it out with a 3D projection from that carbon and then just draw the exact reflection. Remember, the reflection, the mirror image, is always going to be the enantiomer for that chiral molecule. Okay, next question. Label the chiral center in this molecule. Pause the video to have a go at that. Pop them up. Once again, find all your sp3 hybridized carbons, which in this molecule is all of them. Discount all your CH3 and CH2 groups. Now this one here has two CH3 groups attached, so it can't be chiral. And this one on the right hand side, however, does have a CH3, a C2H5, a C3H7 and a hydrogen, so it is chiral. Slightly more difficult now, try that with glucose. Pause the video. Pop them up. So remember, when we have a ring structure, we're going to use symmetry. Now, of course, identifying all the sp3, we can see that the one attached to the OH is not, because it's a CH2 group. The rest of them, we need to draw lines of symmetry through each carbon and see if there's symmetry. And if there is no symmetry, then that would be indeed a chiral carbon. So going round the molecule here, we see all of the carbons at these corners of this ring are indeed chiral. And so we have 5 chiral centers. Lastly, let's finish off with one at expert level. Pause the video to have a go at this one. Pop them up. Going through the molecule and labeling all the sp3 first, and then obviously discounting any CH3 or CH2 groups, we end up circling quite a lot, but then also removing quite a lot initially. The ones we have left over after we've done this process, so if we get rid of all those, all of these we're going to have to check using the symmetry method. As I draw these lines to bisect the molecule at these carbons, I find indeed that all of the carbons in question here have no line of symmetry through the molecule, and so all of these carbons are indeed chiral carbons. Fantastic. So now we've got that done. No videos for practicals here, but there is a lot of practice that you can be getting on with. You need to be able to do this well and also differentiate between the different types of isomerism. Thanks again for joining me, guys. Don't forget to like, subscribe, and share the video. And as always, practice makes slightly better.